When we clear denominators in a rational equation, we multiply both sides by a variable expression, which is something that we avoid if we possibly can. Why is that something to be avoided? Let's try solving this rational equation by clearing denominators and see what can go wrong. So here my denominators are x squared minus 4x minus 12 and x squared minus 2x minus 8. I'm going to want to multiply both sides by my least common denominator. To find that, I need to factor each of these denominators. So on the left, I have x squared minus 4x minus 12. That's a quadratic with leading coefficient 1. So I can use the shortcut. I want two numbers that multiply to negative 12. That'll be a positive number and a negative number. I want them to add up to negative 4. So I think I have positive 2 and negative 6. Yeah, if I multiply that out, I get my original polynomial. X squared minus 2x minus 8, also in the form that lets me use the shortcut. Right, so I'll have, again, a positive number and a negative number. I want two numbers that multiply to give me negative 8 and add up to negative 2. I think I'll have positive 2 and negative 4. My LCD then, I'll need a factor of x plus 2, a factor of x minus 6, and a factor of x minus 4. And I think that's it, right? Those are all my factors. I'm absolutely going to leave that in factored form, right? I don't actually care about that polynomial. That's just what I want to multiply by on both sides to clear my denominators. So let's do that. I'm going to say x plus 2 times x minus 6 times x minus 4 over 1 multiplied by my left-hand side, which I have 3x plus 2 in the numerator. The denominator I'm now going to write in factored form. Right, I factored that as x plus 2 times x minus 6. And then on the right, I'm going to multiply by my least common denominator again. And on my right-hand side, I'll have 2x plus 1 over its denominator in factored form is x plus 2 times x minus 4. So when I multiply this out, on the left, I'll have x plus 2 times x minus 6 times x minus 4 times 3x plus 2 all over x plus 2 times x minus 6. And on the right, I'll have x plus 2 times x minus 6 times x minus 4 times 2x plus 1 all over x plus 2 times x minus 4. And now I'm going to go through and cancel common factors. So on the left, my x plus 2's cancel, my x minus 6's cancel. On the right, my x plus 2's cancel, and my x minus 4's cancel. And that's what I wanted to have happen, right? Everything in the denominators cancels. If I had the right least common denominator, everything in my denominators will cancel out. And now I'm left with, on the left, x minus 4 times 3x plus 2 On the right, x minus 6 times 2x plus 1. I'm left with a polynomial equation. And I know how to solve a polynomial equation. In this case, I'll need to multiply out both sides. So I'll have 3x squared plus 2x minus 12x minus 8 equals 2x squared plus x minus 12x minus 6. Combine like terms on both sides. 3x squared minus 10x minus 8 equals 2x squared minus 11x minus 6. And then I will subtract all of the terms on the right-hand side. So I'll subtract 2x squared on both sides. I'll add 11x on both sides. I'll add 6 on both sides. And I think that gives me x squared plus x minus 2 equals 0. So from here I'll factor. I need two numbers that multiply to negative 2. So one will be negative, the other positive. They add up to positive 1. I think that'll be a negative 1 and a positive 2. That product is 0. So either x minus 1 is 0, which gives me solution x equals 1, or x plus 2 equals 0, which gives me solution x equals negative 2. So I think that x equals 1 and x equals 2 are the solutions to my original equation. Let's check that. Again, just grabbing a copy of that original equation and bringing it down here so I can see it. I'm going to try x equals 1. So that'll be 3 times 1 plus 2 all over 1 squared minus 4 times 1 minus 12. That works out to, let's see, 5 over negative 15, which is negative 1/3. On the right, I'll have 2 times 1 plus 1 all over 1 squared minus 2 times 1 minus 8, which works out to 3 over negative 9, also negative 1/3. So that works out. But look what happens when I try x equals negative 2. I'll have 3 times negative 2 plus 2 over negative 2 squared minus 4 times negative 2 plus 12. That's going to work out to, negative 4 over 0. That's undefined. What happens on the right? 2 times negative 2 plus 1 over negative 2 squared minus 2 times negative 2 minus 8 is, negative 3 over 0. These are both undefined. Negative 2 can't be a solution to the equation, because when I plug in negative 2, I get just nonsense. Only x equals 1 is a solution to my original equation. What happened? Well, here's what happens. When x equals negative 2, remember my LCD? X plus 2, x minus 6, x minus 4. If I plug in x equals negative 2, that'll be negative 2 plus 2 times negative 2 minus 6 times negative 2 minus 4. That's 0. If x equals negative 2, my LCD is 0. So when we multiplied both sides by that LCD, we accidentally multiplied both sides of the equation by 0. Obviously, if we multiply both sides of an equation by 0, we're going to get 0 equals 0, which is true, but not interesting. So that number that showed up as a solution in the process, but only showed up because we multiplied both sides by 0, x equals negative 2, is what's called an extraneous solution to this equation. An extraneous solution is one that shows up in the solving process, but wasn't actually a solution to the equation. We're going to see several reasons why this can occur, but the reason that we just saw, the reason that shows up with rational equations, is that maybe we accidentally multiplied both sides by 0. If we accidentally multiplied both sides by 0, we're going to get an extraneous solution. That wasn't really a solution to the original equation, so when we realize that we got one, we throw it in the garbage. In this example, x equals 1 was actually the only solution to the equation.